In the first video, we saw that the Weierstrass representation is an algorithm for making minimal surfaces in R3. It involves holomorphic data as input and is essentially solving an ODE in the form of an integral. In this video, I would like to introduce the DPW method, which is also an algorithm for making CMC surfaces in R3. It also involves holomorphic data and solving an ODE. In the last part, we will see that the DPW method can be adapted in order to make minimal and CMC surfaces in the three-dimensional sphere S3 and in the three-dimensional hyperbolic space H3. Some definitions first. Recall the example of the helicoid and the catenoid in the first video. These two surfaces belong to the same family called the associated family and was indexed by a spectral parameter lambda in the unit circle S1. The DPW method needs to construct the whole associated family of a CMC surface in order to work. Therefore, every object that we will handle will actually be a map from lambda in S1 to some space. And the set of maps from lambda in S1 to some space will be called a loop space. As an example, I have written here the definition of a loop algebra. If G is a Lie algebra, the loop algebra, denoted by lambda G, is an infinite-dimensional Lie algebra composed of smooth maps from S1 to the Lie algebra G. Any loop in this loop algebra can then be decomposed into its Fourier series, with coefficients gi. And as for the associated family, the variable lambda is called the spectral parameter. This is sufficient for us to define what is an admissible DPW potential for the DPW method. A holomorphic one-form eta from a Riemann surface M to the loop algebra S02C is an admissible DPW potential if these two conditions are satisfied. First, if you expand the potential into a Fourier series, you must have only powers of lambda which are greater than -2. So the worst you can have is lambda inverse. Secondly, the coefficient in front of this lambda inverse must be a nilpotent matrix. Besides loop algebra, we will also need loop groups. Look at the upper right corner of this slide. I have written the loop group lambda SL2C. This set is the set of smooth maps from lambda in S1 to the set of matrices SL2C. One can define a subgroup of this loop group composed of loops B such that B extends at lambda equals 0 and such that B at lambda equals 0 is of this form, with X being a positive number. Defining this loop group is necessary for the second step of the DPW method, which involves an Iwasawa decomposition. Think of Iwasawa decomposition as a loop group version of the QR decomposition of a matrix in SL2C as an orthogonal matrix Q and an upper triangular matrix R. This decomposition has an equivalent for loop groups, which is exactly given by this theorem. Multiplication between an element in the loop group lambda SU2 and an element of the group defined above is actually reversible. Any loop in lambda SL2C can be decomposed into the product of a loop in lambda SU2 and a loop in lambda SL2C plus R defined above. This decomposition is called Iwasawa decomposition. The first factor will be called the unitary part and the second factor will be called the positive part. Now we have everything that we need for the DPW method. The DPW method is also an algorithm and as such takes input data. As with the Weierstrass representation, we need a Riemann surface M together with its universal cover M tilde and the corresponding projection. We need a base point Z0 in M tilde. And because the first step of the DPW method is to solve an initial value problem, we need an initial value phi naught in the loop group lambda SL2C. Of course, we also need a DPW potential eta, which is a holomorphic one-form from M to lambda SL2C. With these ingredients, the DPW method has 3 steps. First, define a map phi from M tilde to the loop group lambda SL2C as the solution of the following initial value problem. You solve an ODE on M tilde d phi equals phi eta with initial value phi of z0 is phi naught. The resulting map phi is holomorphic and is called the holomorphic frame. The second step is to perform an Iwasawa decomposition on phi. For each z in M tilde, decompose phi into a unitary part f and a positive part b. This defines a map f from M tilde to the loop group lambda SU2, which is not holomorphic anymore and is called the unitary frame. Finally, the last step is to apply a Sim-Bobenko formula on the unitary frame big F. For each z, taking f, differentiating it with respect to lambda, multiplying it with f inverse and applying the coefficient minus 2i over h, will give you a map f from M tilde to little SU2, which, as in the first video, will be identified with the Euclidean 3 space. Let me summarize. The first step is to solve d phi equals phi eta. The second step is to perform an Iwasawa decomposition of phi into fb. And the third step is to apply the Sim-Bobenko formula. The theorem giving its name to the DPW method is the following. The algorithm above produces conformal constant mean curvature immersions into R3, the mean curvature being the number h that you chose in the Sim-Bobenko formula. And similarly to the Weierstrass representation, the converse is also true. Any conformal constant mean curvature surface into R3 can be locally constructed this way. The DPW method is a bit more complicated than the Weierstrass representation, but what you have to remember is that it is the same style. Starting from holomorphic data eta, you solve an ODE and apply some formulas to get a CMC immersion. Let's have a look at the simplest non-trivial example. Taking the whole complex plane as a Riemann surface with the following initial values for our ODE, and taking this potential, you can follow these 3 steps and compute everything explicitly in order to get at the end the following immersion. F is the stereographic projection from the North Pole composed with a translation. Here I've taken mean curvature h equals 1 and the value for the spectral parameter is lambda naught equals 1. I know that this seems to be a very twisted way of making a sphere, but stay with me, you will see that this method is very powerful in order to make non-trivial examples. Let me also recall that this is the simplest possible DPW potential. It is a trace-free matrix of holomorphic one-forms depending on a spectral parameter lambda, such that in the Fourier decomposition, the coefficient in front of lambda inverse is nilpotent, and such that you don't have any lambda minus 2, lambda minus 3, and so on. Now, in this example, the Riemann surface M is simply connected. But if you remember the last video, we may have some period problems if we take a non-simply connected Riemann surface in our input data. So what happens if M is not simply connected? Let's try to make a simple example and take for the Riemann surface the complex plane minus 1 point. As a base point, take z0 above 1, and to keep things simple, let's take the identity as an initial value. For our dpW potential, we will take a meromorphic one-form with a simple pole at z equals 0. Let's try that with a random value for A, satisfying the condition of dpW potential. Similarly to the Weierstrass representation, the dpW method is an algorithm which you can implement into a computer, and similarly to the Weierstrass representation, Nick Schmidt in Berlin did that with his software XLab. This is what happens if you take a random value for your dpW potential on a non-simply connected Riemann surface M. You see that you get an immersion from the universal cover of M into R3. This immersion is CMC, but this immersion doesn't close itself. So it's not well defined on M, only on the universal cover M tilde. We thus have a period problem also in the dpW method, and because the first step of the dpW method is to solve an ODE of this form, the period problem will take the form of a monodromy. Take a closed path gamma in M with base point pi of z0, and take any z in the universal cover M tilde. Then the monodromy of the closed path gamma is a z-independent matrix M of gamma depending on lambda with value in S02C, defined by the following formula. By lifting gamma from M to M tilde, the closed path gamma now acts as deck transformations on points of M tilde, and the difference between phi after a deck transformation and before a deck transformation takes the form of the monodromy M of gamma. Now, let's say that you have a holomorphic frame on a non-simply connected Riemann surface, such that M of gamma is always the identity. If you had that, then the deck transformation would not do anything to the holomorphic frame, and because the holomorphic frame would be the same after or before the deck transformation, you would get a well-defined immersion F. But this never happens. The monodromy of a closed path is generally not the identity matrix. Nevertheless, you have sufficient conditions so that these three steps still gives you the same immersion F before or after the deck transformation. And these sufficient conditions are written here. If for all closed path gamma in M, these two conditions are satisfied, then F is not only defined on the universal cover of M, but it is well defined on M itself. In this case, you have closed the period. This set of equations is called the monodromy problem, and it is at the core of the desingularization procedure that I will show you in the last video. So let's go back to our previous example, which did not close. Remember that the Riemann surface is the complex plane minus 1 point. These are the simplest possible initial values you can take, and we want a dpW potential of this form. In 2007, Schmidt, Killian, Kobayashi and Rossmann found sufficient conditions on A so that the monodromy problem is solved. As an example, you can take this form for A with R and S real numbers satisfying this simple equation. Let's look at the resulting surface. Now that we have taken good values for our dpW potential, solving the monodromy problem, our CMC surface is now well defined on the complex plane minus 1 point, and not only on its universal cover. This makes a Delaunay surface, CMC surface, in R3. Remember that you even have freedom in the parameters R and S in the dpW potential, which allows you to deform the Delaunay surface by changing its weight. So this is a Delaunay surface with very small weight, and you can increase this weight to have a one-parameter family of Delaunay surface, converging to a nice cylinder. So the DPW method allows us to construct constant mean curvature surfaces in R3. This completes the picture we had before with the Weierstrass representation allowing us to construct minimal surfaces in R3. But the DPW method itself can be adapted and extended. By changing only the last step of the DPW method, the last step being applying the Sim-Bobenko formula, one can construct these classes of surfaces. Constant mean curvature surfaces with mean curvature greater than 1 in H3, the hyperbolic 3 space, and all the constant mean curvature and minimal surfaces in the 3 sphere. One great benefit of this theorem is that it involves only changing step 3, which means that we could take as input data the data giving rise to a Delaunay surface in R3 and make Delaunay surfaces in H3 and S3. This is something that Schmidt, Killian, Kobayashi and Rossmann did, and you see that the input data is exactly the same. Up to some minor difference is that in order to solve the monodromy problem, you have to take your ambient space into account. And so the equation that the numbers R and S has to satisfy is not the same whether you are in the Euclidean space, the hyperbolic space, or the spherical space. Here is the equation for hyperbolic 3 space, and let's have a look at the resulting surface. This is a Delaunay surface in the hyperbolic 3 space, which is given here in the Poincaré ball model. The DPW method has been used a lot to construct new examples of CMC surfaces in the 3 different space forms, R3, H3, and S3. Because it involves holomorphic data, it is quite rigid, and you can really have control on the resulting surface if your input data is not too much complicated. Let me show you, for example, a tetranoid in R3 made by Nick Schmidt. Again, this is made with the DPW method. This is a constant mean curvature surface in R3, and it is a well-defined immersion from the Riemann sphere minus 4 points to R3. One has to solve a monodromy problem using the symmetries in order to make this surface close. So in this video we saw another Weierstrass type representation called the DPW method, which allows for the construction of these 3 classes of surfaces. Thank you for watching, and see you in the next video when we will look at a desingularization procedure in order to make more involved examples.